In this video, I want to spend a few minutes to review some terminology from previous classes. So this should all be material that you've seen either in SER200 or CSE 205 or MAT 243. Hopefully none of this is new. I'm not going to spend all that much time on it. Really what I want to do is just make sure we're kind of on the same page. So the first thing I want to talk about here is what we call N, or the problem size. So a lot of times, we have an algorithm. This algorithm has a bunch of inputs, and those inputs maybe have different types, right? Maybe I give it a number, maybe I give it a list. Well, the list in particular is a little bit interesting because basically that algorithm, right, will take a different amount of time to run, whether that list has, one thing in it, or 10 things in it, or 20 things in it. There's a dependency between the algorithm and its input. And so that list that's maybe being processed, right, we have to care about how big it is, right? And so what we'll say is that it's size n, and in fact, it defines the problem size. I'm just using lists here as an example. It also could be something like an array, right? So if you think back to something like insertion sort takes an array to be sorted. The problem size is the length of that array. And so we'd say the length of that array is n. Now, typically an algorithm will have multiple inputs. Some of those will just be something like a number. A number doesn't really count as problem size. The reason for that is that adjusting that number typically doesn't change how long that algorithm takes to run. So maybe that a number is something like a cutoff. Throw away all the values less than n or less than k, right, in this input list. Well, what we choose for k really doesn't matter all that much, right? It's a cutoff. It'll always be applied the same way. Versus if I have a list going in, right, and it has different number of elements in there, well, the algorithm has to do more work if there's more elements, right? And maybe it's doing something like sorting, right? In which case, basically, your problem, right, is I have to move around more things, right? That's clearly more work versus just changing what is the cutoff or the threshold that's being enforced in something else. So some inputs really matter, some don't. Some basically treat as constants because they don't affect the running time of the program. But when you have a collection, right, an array or a list, then we care about it. And typically what we say is that that defines the problem size, right, an n. Sometimes if you take in more than one collection, you'll say maybe you have m and n, right? That depends on the size of two things. So n can vary in a lot of different ways. We've just talked about collection size. Maybe that's something like sorting. Another thing we could have, if maybe we were talking about a recursive function, is maybe we do have an integer, but that integer actually does impact how long the algorithm takes to run. So let's say something like the recursive factorial. In recursive factorial, the value of that parameter is going to control how many recursive calls you make. So the larger that number, the more calls you will make, right? Lower number, fewer calls. So that actually does change the algorithm's performance. It's not just inside of an if statement that does cuts out all these values less than k. Right, it's actually having some impact on the number of times that function loops or the number of times that function calls itself. Now, in that case, that algorithm is actually dependent on that input. So in that case, it would be fair to say that that's part of our problem size, right? So the factorial number, maybe we're taking factorial of I, that also doubles as our problem size, and then maybe we just call it n, because that's how big our problem is, right? We're trying to compute the factorial of 10, and it's going to take me basically 10 steps to get there. So that's another idea of size. The last example here is in terms of strings. Maybe I have an algorithm that reverses a string. Well, in that case, I'm going to need to go through and touch every character inside there and change its position. Well, again, right, that algorithm is going to take a different amount of time to run, whether it has 10 characters or 100 characters. There's some sort of dependence between the length of that input and how long the algorithm takes. So again, that would be kind of fall under things that we need to care about, how big they are, right? Because it defines our problem size. So in general, right, an algorithm, right, is going to be defined over some set of parameters, and then some of those parameters are going to have some sort of size associated with them, right? And those sizes are what we're going to have to keep track of if we're trying to figure out how this thing acts, because how long it takes to run will vary with those sizes with the sizes of the parameters that are going into it. All right, so that is our idea of n, our problem size, right? How big is something? How much work do I have to do? The next thing I want to talk about is growth functions. So growth functions have kind of a specific meaning. So growth functions are really just some f of n, right? So they're some function. The significance, though, and why we call them growth functions is because growth functions are showing how a function grows in terms of operations. So the typical f of n is counting up a number of operations. And really, though, we should be more specific there. We want to count up some specific action, right? Some specific thing the algorithm is doing. For now, I'll just say operation, so you can assume that maybe it's executing a line of code, right? The number of things that have to happen, the number of instructions that need to be executed on the CPU, something like that. Well, a growth function is basically a normal function, right? That's meant to count up how many operations will be required for a given input size, right? So I can say, hey, I have an input array of size 10, and then my growth function will compute for me, that means it'll take 100 operations for you to process that. That is the basic idea of a growth function. It's giving us a way to calculate the number of operations from the problem size. So we're linking n to the amount of work that needs to be done. So for a lot of analyses, usually what we want to do is we want to find out what is the growth function. And that's something you hopefully have done in a previous course, is actually write a growth function from a bit of code. We'll be doing it again here in this course, but hopefully you've done it before as well. As some quick examples there, I have down there f of n equal 1. As an example of a potential growth function. What that is saying, okay, I have a growth function that no matter what input I give it, it always takes one operation to complete, right? So it's maybe something that doesn't do very much, right? It just does a fixed amount of work. Maybe it adds a number, right? Maybe it just increases something and that's really just one line of code, right? Or it returns something that's just one line of code. Very simple. Versus I have something like f of n equal 1 plus n. What that's saying is, oh, you're doing a little bit of work, right? You're doing one operation plus n other things, right? So maybe that's where you're going through a list and maybe you're increasing everything in it, right? You need to go and touch every element in there. In that case, that n parameter, right, the problem size, is based on the size of that input collection, right, the number of elements in that list. And so as that list gets bigger, right, the growth function is going to basically grow. Every time you add 1 to the input size, it's going to take one extra operation to process it. So in that case, right, basically our growth function, right, varies as our input size does, whereas in the first example, it does not vary, right? It's constant amount of operations are executed based on any input. And really there in f of n equal 1, it's a little bit awkward because that n is still there, right? So we're still saying that the problem size can vary, but somehow there's just no link, right, between that and the number of operations it takes to run. So it's a little bit awkward, but we do see that in some cases. As a final note here, one thing that's significant about growth functions for us in this course is the growth functions are meant to be exact. So they should exactly tell us how many operations are going to be required or maybe how much time will this algorithm take, right? So they should be exact solutions. They are not intended to be approximate. For approximate, we have something else. We'll have different names of things. Growth function is supposed to be exact. The last bit of terminology I want to talk about is big O. So big O means something like O of 1 or O of n or O of n squared, right? Or O of n cubed or O of n to the second or whatever. You should have seen this before in a previous class. These are all big O expressions. Maybe I would call them big O terms. They're using what is called big O notation. What big O notation is it's a way to write an inexact quality, an inexact quantity. So O of 1 is basically saying, oh, it's just some number. O of n is saying, oh, it's some number times n. So I'm not giving a specific number. I'm not saying it's 2n or 4n or 5n. I'm just saying it's something that's a multiple of n, right? Grows like n with a constant in front. And so basically, big O is used as a summary, right? So you can look down there at that expression I have. So I have the expression 2n plus 15 equal O of n. What that's saying is that expression 2n plus 15 is big O of n, right? So 2n plus 15 is O of n, right? So basically we're saying, oh, hey, this function, right, as I change the value of n, it's going to basically act like a linear function, right? It's going to act like just n. In the full function, that plus 15 is in there as well, but it really doesn't matter. It's a constant. It's going to be small, right? If n becomes really large, we don't even, the impact of that 15 doesn't really matter. And then just for convenience, right, big O is basically hiding an invisible coefficient in front of that letter, right, in front of that variable. So that 2 kind of goes away as well. Now, if we had something else, like for example, 10n plus 2, that as well would be O of n, because again, it's just some expression that varies with some multiple of n, right? Inside that, the little expression, right, that's inside that O notation. So overall, right, big O is giving us, right, this way to basically write a quantity, right, that varies a little bit, and somehow there's also this typical notion in there that it's going to be larger than something. So that big O typically is representing what we call an upper bound. We'll talk about that a lot more in a minute. That's going to be some value, right, that somehow always stays above something else. So big O of n should always stay above, right? Picture you have a graph in your head, right? It'll always stay above that 2n plus 15. So that's what we typically use big O for, is it represents upper bound on something. It shadows something. A final note there is that we typically use big O in terms of long-term behavior of a function. So once our input size gets really big. For various reasons, and we will talk about them, it's hard basically to compare functions or talk about functions when their input size basically is really small. So it's like 0, 1, 2, 3, 4. Somehow things are going to be a little bit noisy. You can look at that graph on the right maybe to get some conceptual idea there. So big O somehow is used generally when we expect n to be sufficiently large. I'm using air quotes there because sufficiently large isn't really defined. It's just what people say.